Okay, so we are going to start the second session, which is about, as we said, once we have some estimate of the uncertainties, how to propagate them through complex data processing and modeling. And so I'm going to start with a presentation myself about techniques to propagate uncertainties through data processing. And so it's a presentation that will be illustrated by the work of two young researchers that work with me. So Lara Pantoni, who gave a talk on Monday, and Dongling Hu, who is going to give a talk this afternoon, actually. So the fact that in many situations, we need to propagate uncertainties through complex nonlinear operations. And in practice, the cases that interest me is, for example, when you need to analyze a multi-wavelength set of images, and you want to compare them. So it means you want to look at the same physical region at different wavelengths, so in different images with different field of view and different angular resolution. So you need to propagate those uncertainties through, in particular, there are more steps, but a complex background subtraction that implies subtracting stars, cirruses, and background galaxies, then degrading all the images to a common resolution by convolving them with a kernel, and also reprojecting those images on a common grid, so resampling them. So that's one first application that interests me. And the other one, it's a derivative of that in spectral analysis, when you have a spectral cube, and you want to also degrade the resolution of each wavelength, because usually you have different angular resolution at different wavelengths when you have a typical spectral imager. Also, we project them on the same grid, and also the particularity of spectral analysis is that you also want to do line fitting to extract a line flux, on these things. So these different steps, what they do is that they will change the uncertainty, so they will change the noise level. Also, its distribution. Even if you have Gaussian noise at the beginning, you are not going to necessarily have Gaussian noise in the end. And also change the correlation, of course. So I'm starting with first an example from multi-wavelength image homogenization from Lara Pantoni's work. So this is IRAC 8 microns with a Spitzer image of the galaxy M99. So first, if we try to look at what is the noise in the background of this galaxy, so masking the galaxy and looking at the distribution of the flux in the background, which provides a relatively good estimate of the noise in these images, you first see that actually it's not Gaussian already, because you have a bump here. This bump is due to background galaxies and residual cirrus emission that we could not perfectly subtract. So right away, you see that you don't have a Gaussian noise. And then what we want to do is that we want to compare those two images consistently. So it means that we want to degrade this image to the resolution of this one and resample it on the same pixel grid. So if we degrade it, it looks like that. And then if we resample it, it looks like that. And so to achieve these steps, I mean, to propagate the uncertainties through these different steps, there are several methods. So the first one is possible, actually, in many cases, to derive analytical formula to propagate these uncertainties. So the advantage is that it's relatively quick to run, and it's also elegant because it's analytic. But the problem is that it usually, and often requires some approximations about the normality of the noise, about also the shape of the kernels when you account for convolution. So that's it means that you need to make approximation about something that might not be negligible. And also, it can become excessively complex if you want to account for several steps, and steps that are actually complex to account for. So a more applicable method, it's to perform some bootstrapping. So it's a Monte Carlo method. So it's a type of frequentist approach. And basically, it consists in, as long as you have a series of reproducible steps. So what I told you, convolution, reprojection, you simply loop over these steps and add some random perturbation at the beginning, on the flux of your data. And in the end, instead of having one flux per pixel, you have a distribution of fluxes. And distribution can allow you to estimate all the parameters of the noise of this data. And so the advantage is that it's very easy to implement because it's simply a big loop over your data. You can account for any effect that you can do in a reproducible way. And you can really account for the complexity of the noise or the non-Gaussianity and correlation. And I'm going to demonstrate that. And one of the problems is that it can be long to run depending on the processing that you perform, especially if you have large images. Basically, whatever you do, you have to do it a large number of times to get a statistical sample, so like 100 times. And it's also not completely rigorous because it's not centered, because you are adding random perturbation to a point that is already having an error. So it's always the frequentist Bayesian discrepancy. And you have also Bayesian modeling that is possible. That's the most rigorous approach because this time you recenter your emission. But the problem is that for this particular case of multi-wavelength homogenization, it's quite difficult. And in my case, I'm not sure if it's really realistically feasible because it means that you would need a parametric model of the morphology of your galaxy to do that. So in what I will follow, I will focus on the demonstration of the bootstrapping method. So talking about the images of M99 that I showed you, if we're going to look at the noise to signal ratio pixel per pixel. So here it's going to be very noisy pixel, and here high signal to noise ratio, and the correlation between adjacent pixels. So at the first step, so in the original data, you have this distribution. So it's not the same distribution as I showed you before, which was really the intrinsic distribution of the noise. Here it's the distribution of the standard deviation of this noise for the different pixels. So it means that you have noisy pixels here, and this is basically the center of the galaxy. And the correlation between adjacent pixels corresponding to that in the original steps is this one. And so if you are used with statistics, you know the shape of this curve because it's the correlation coefficient that you get from a random, distribution of independent variable. It's a Wishart distribution. So that's the original data. So now if you perform convolution, what convolution is doing is that it's smoothing the data. So it means that you are averaging the flux in many pixels. And so that's why that on average, you are actually increasing the signal-to-noise ratio. So you are reducing your noise. So that's why the distribution is now here. However, if you measure the total flux of the galaxy, you will have the same uncertainty in this case and this one because you have the same amount of information. And so the subtlety is that in the case of convolution, now what you see, you probably don't see, is that the correlation distribution is actually centered around one. It's very narrow. So it's in my particular case, this is because the size of the kernel convolution is actually much larger than the typical pixel size. So that's why it's so correlated. But so it means that we have traded off, we have gained some signal-to-noise ratio, but everything is correlated now. And so that's why I told you that the uncertainty of the integrated flux in this case will be exactly the same. Yes. And now if we go to the last step, so the resampling, so you see that in my particular case, we don't change much the distribution of the noise, but we simply have larger pixels. And so it means that now we are a bit less correlated. So that's the distribution of the correlation. And the idea is that once we have done all these steps, we have this distribution of noise and all this correlation, we can feed that to a Bayesian SED model and account, those uncertainties that have been propagated as best as we could. So that's a way, yes? No, so it's a spatial resampling, yes. So it's reproduced on a different pixel grid there. Yes. So those are, the propagation of the uncertainties through the different data processing step, but also other interesting effects that you could put into, account for is some of the biases of the telescope. And I can illustrate that with the pointing error so those are data from the Dongling-Hu's project. And so you see here we have a spectral map. So this is a map of the galaxy M83 obtained with the Spiegel IRS telescope. So we have one spectrum for each pixel in this map. You see, for example, for the central pixel, you have one spectrum. We have one noise distribution corresponding to the different steps that I just showed you before, to the propagation through convolution and reprojection. What we also know is that actually the IRI spectroscopers have pointing uncertainty. So it means that it's slightly jiggle around the source. And that's actually something that we can actually simulate, randomly the same way. So when we jiggle around a bit this image, it results into an additional term of uncertainty that actually looks like that. And in this particular case, it actually dominates the noise budget. So that's a way to demonstrate that even with this method, we can account for also other biases that are due to the way the observations are performed. So as a takeaway of this small presentation, so as I told you, several applications require heavily processing original data. And we can account for this processing step and some biases. And I try to show you that the bootstrapping method is very efficient and quite easy to implement because you just need to add random parameters, perturbation, loop over the whole process, and compress the distribution only at the end to preserve all the information. And we get a full uncertainty distribution. Thank you.